The objective of this video is to establish design procedures for single and double layer fractional slot windings. So far in the winding design unit, we've constructed design procedures for integral slot windings. And by design procedure, we mean a discrete set of steps that you follow to determine where the coil sides of a phase winding should reside in the stator. In this video, we are now going to establish these design steps for fractional slot windings. And we'll have to consider the case of a single layer winding separate from a double layer winding. And we're going to start by talking about the double layer winding because the fractional slot design procedure for a double layer winding is nearly identical to the design procedure for an integral slot double winding. And then from there, we're going to build up and talk about why we have to modify the design procedure for single layer windings, and finally propose a set of steps that we will use to design single layer fractional slot windings. So, starting with the double layer winding. And the first step for designing a fractional slot winding is that we need to check the symmetry conditions. We need to specifically check these two conditions that I've put in blue. The first condition is making sure that we have an integer number of coils per phase, and we can check that by making sure that 2 times p divided by n is an integer. And the second condition is that we need to make sure that n is coprime to m. If these conditions are a surprise or confusing to you, I encourage you to go back and review the video on symmetry conditions for fractional slot windings. Our second step is that we will use the star of slots to place coil sides in the top layer. This is identical to the double layer winding design procedure. And our third step is that we will determine the pitch or the span of our coils in order to determine where the coil sides of the bottom layer should be placed. And these last two steps are identical to the steps that we do to lay out an integral slot winding. The only difference for the fractional slot double layer winding is that we need to carefully check our symmetry conditions. Remember, for an integral slot winding, the fact that Q is an integer means that it satisfies the symmetry conditions. For the fractional slot winding, we have to manually check these expressions. So before we move on to single layer windings, I want to talk through a simple example. And this example is going to be a 6-slot 4-pole design, and we'll use these design steps to lay out the winding. And then we'll talk about why these design steps need to be modified to facilitate the design of a single layer version of that winding. So our first step in designing this winding is that we need to check the symmetry conditions. Why don't you go ahead and try this on your own, press pause and press play when you're ready to watch me check the symmetry conditions. And our first symmetry condition is that 2p divided by n must be an integer. And in fact, we find out that this value is 2, which certainly is an integer, and that means we've satisfied the first symmetry condition. The second symmetry condition is that n must be coprime with m, and indeed 2 is coprime with 3, which means we've satisfied the second symmetry condition. And therefore, our winding is symmetric. And our second step is that we must use the star of slots to lay out the top layer of our winding. Again, why don't you go ahead and practice this on your own, press the pause button, and press play when you're ready to watch me do it. And so you can see we've got this star of slots where coil sides 1 and 4, that is the top coil sides in slots 1 and 4, belong to the U plus, belong to phase U in the positive direction, that is going into the page. And similarly, phase V's got coil sides 2 and 5, and W has coil sides 3 and 6. What you notice here is that in this star of slots, we have no coil sides assigned to phase U, V, and W coming out of the page. And that's okay because this is a double layer winding, and we know that the coil is going to span over to the bottom layer, so the return path for these coils is going to be in the bottom layer. And so in step 3, we need to determine the appropriate pitch for our coil. And so why don't you go ahead and try this on your own, and then you can see me do it and what I propose for the coil pitch. So press pause and press play when you're ready to watch me do it. Okay, so you can see that it is impossible to make this be a full pitch coil, and that's a characteristic of fractional slot windings, is that M times Q is always going to be a fraction. And so then we need to we need to round this number in some way. And so what we're going to do is we're going to round it down to the nearest integer, because that usually is preferable. We have a shorter length of N connection, and when we do that, we end up with a pitch of 1 slot. And you'll notice that this translates to a concentrated winding. This is a concentrated fractional slot winding because our coils just directly wrap around a tooth. We also call this a tooth coil. And this is a very popular class of fractional slot windings because they're easy to manufacture, and you can get a higher fill factor. You can get more conductors in the slot. At this point, we have all the information that we need to sketch the winding schematic. So let's go ahead and do that for phase U. And press pause, try it on your own, and then press play when you're ready to watch me do it. And so your winding schematic should look like this. Alright, so we have completely laid out this double layer fractional slot winding, which is the case of this 6-slot 4-pole 3-phase winding. What I want to do now is I want to go back to looking at our zone distribution, our phase zone distribution, and where the slots reside within those phase zones. So let's go ahead and we're going to sketch this. Okay, so what I've done is I've sketched a 4-pole rotor, and then coming out from the rotor radially towards the stator area, I've labeled our phase zones, and this is something that we've been doing in previous videos. And so you can see I've been using the sequence that we always use when we lay out our windings. We start with a phase zone of U plus, and then W minus, V plus, U minus, W plus, V minus, U plus, and then we repeat a second time because we've got 4 poles. And again, this is the same thing we've been doing when we've introduced our winding design unit. We started by drawing these phase zones and we migrated to using the star of slots instead. So the star of slots exactly translates to the phase zones. It's just that the phase zones are more of a magnetic way of looking at it, whereas the star of slots is more of an electric way of looking at it because it looks at our voltage phasor. So what I'm going to do next is I'm going to draw on here our individual slot locations and then show how they've been allocated to different coil sides. So we're kind of peeling back the onion, so to speak, to look at what our design procedure has actually done, where these coil sides reside relative to where we said we would ideally place coil sides in our phase zone diagram. And so the first thing to notice is that we've drawn our slots where they appear on the stator. So we had said there's going to be a 60-degree spacing between slots. So indeed, starting from 0 degrees with slot 1, moving 60 degrees counterclockwise, we have slot 2, slot 3 is another 60 degrees, slot 4 is another 60 degrees, and so on and so forth. So what we can notice from this is that similar to our star of slots diagram, missing coil sides in the negative regions of our phase, we can see that the same thing is occurring here. In the negative phase zones, we have no slots located. And so we already immediately know that our layout does not truly place the coil sides where our phase diagram might prefer them. So we prefer to have one coil side here in the U plus region, and then the return coil side over here in the U minus region, but there's no coil side there. That would correspond to a full pitch coil if it could indeed go from here over to here. But what we said in our layout is that we're going to span only one slot, so it's going to go from here over to here. And so let's draw that. In fact, the same thing happens for all of our coil sides. If it was a full pitch coil, it would be placed in the negative phase zone, but since that is not possible, it gets short pitched by a half a slot. And so what this is building up to is thinking about what it means to lay out a single layer winding. Because in a single layer winding, we traditionally would use our star of slots to identify our positive and negative phase bands. But in this case, there's no coils that are residing in our negative phase band. So where should we have the return coil side for a U plus coil? And again, looking at our phase diagram, we can see that we have this problem magnetically. So we put a slot here. So in a single layer winding, we've eliminated this back layer. Where should our winding return? Can we use this slot? Should it span over here? What should we do? And you can squint at this long enough and probably figure out what you should do, but we want to come up with a formal design procedure with a formal set of steps that will always produce a symmetric winding with good winding factor, regardless of how many slots and how confusing it is to look at. And what we're going to do is we're going to go back to thinking about this in terms of our a phase zone diagram. And so the question at the moment is how should we design this 6-slot 4-pole motor as a single layer winding? As with the double layer winding, our first step is going to be to check the symmetry conditions to make sure it is possible. So let's go ahead and do that. Let's make sure that we can actually design this as a single layer winding. And so for a single layer winding, we check the condition that P by N must be an integer. In the double layer winding, we were checking the condition that 2P by N needed to be an integer. But for the single layer winding, this 2 is gone, and that's because the single layer winding has half the number of coils. So we passed that test. P by N is an integer, is equal to 1. And the second check is the same as it was for the double layer winding, that N and M need to be coprime. And clearly N and M have not changed, so 2 is coprime with 3, and we also pass this test. Okay, so our symmetry conditions tell us that it is indeed possible to design this as a single layer winding. And now let's come up with how we are going to do that. And the fundamental problem that we're having with our current approach is that our star of slots does not have phasors for these zones. So what to do? And the answer is that we're going to go back to using our phase zone diagram. Phase zone diagram is this. And our idea to do this is going to be that we will achieve our value of Q in an average sense. We're going to distribute our coil sides amongst these different zones, or maybe a better way to say that is that we're going to distribute these zones amongst our coil sides, amongst our slots, at uneven spacings, so that in an average sense we have Q slots per pole per phase. Remember, Q is indicating on average how many slots are within a phase band. So you can see right now Q is equal to 1/2, so that means that we have an average of 1/2 of slots residing within any individual phase band. And that's true, right? Because we have one slot over here and then no slots here. So if you take the average of that, that's equal to 1/2 slot. And so now we have to start talking about the number of slots that reside within a phase band, and we will have this be a local quantity. So for phase band I, it has Q slots residing within it. So you can see right now in this diagram up here, phase band 1 has 1 slot, phase band 2 has a Q value of 0, phase band 3 has a Q value of 1. So Q becomes a local concept. It starts to refer to how many slots are residing within a phase band, and our phase bands are no longer going to be have a span of strictly this expression. They're no longer always going to be 180 degrees divided by P times M. And to do this, we're going to introduce some new vocabulary. Coil group is going to be defined as the collection of coils within one phase zone. And so for our simple case up here, there's a coil group of coils that reside within phase zone 1. Now if we had multiple slots, we'd have multiple coils. But here you can see for single layer winding, where we don't have this bottom layer, we just have a single coil that is residing within this phase zone. But if we had multiple slots, then we would have, so here we've got 2 slots, and we'd have two coils that reside within this phase zone, and those two coils together are referred to as a group of coils, or a coil group. And that group of coils consists of Qi coils, where Qi is the number of slots that are within that phase zone. So, just to be clear about this, we're saying that each phase zone is going to have Qi slots, and a coil group refers to all the coils that are placed within that phase zone. And since each slot contains a coil group has Qi coils, which is the same number as there are slots within that phase zone. And we need to have at least n coil groups in order to achieve an average of Q. So remember, Q is this fraction, and it can be expressed in terms of z by n, where z and n are coprime. And so the only way that we can get this average value of Q from an integral number, from a set of Q's that have an integral number, is to have n of them. So our approach is that we have to figure out how many coils belong in each coil grouping. So what we'll do then is that we'll distribute the coil sides of these coil groups across the zone diagram. Or maybe put in a different way is that we're going to determine the relative widths of our zone diagram so that we achieve this sequence of coil groups. And we're going to formalize this in a set of steps next. And again, we managed to distribute these coil sides by adjusting the span of each zone so that it contains Qi slots, where Qi is this number of slots. Okay, so that's the narrative of what we're trying to do. Let's now set up a set of steps that will achieve this. And just like in the double layer winding, we need to check our symmetry conditions, and the key condition to watch out for is this condition, which is different than the double layer winding. Remember, the double layer winding was that we needed to have 2p by n be an integer, while the single layer winding requires that p by n is an integer. And the second step is that we are going to express Q, our slots per pole per phase, as equal to an integer g plus a fraction z prime by n. So remember, little q we express as z by n, but now we're going to reduce this down so that we express it as an integer plus a fraction, where z prime is always less than n and z prime still remains coprime to n. Suppose that we had q equal to 5/2. We would in this way write it as being 2 plus 1/2, where z prime, this is z prime is 1, g is 2, and n is 2. Alright, step 3, part A, is that we pick z prime coil groups to have Qi equal to g plus 1 coils. So remember, we're going to have n total coil groups, but z prime of those will have g plus 1 coils in them. And you see that I put coil groups and coils in square brackets. The reason that I did this is because you can equivalently say that we want to have z prime phase zones with g plus 1 slots in them. It's the same thing, and I want to draw attention to that to help you visualize what we're talking about here. So that's part A. Part B is that we need n minus z prime coil groups to have Qi equals g coils. And again, I put this in square brackets because this is equivalent to saying that we need n minus z prime phase zones with Qi equals g slots. And when we set these up, we want to alternate the number of coils between consecutive coil groups as frequently as possible. And this is like a rule of thumb. This is I'm telling you that this is a good thing to do. The winding will work even if you don't do this. But if you do alternate the number of coils between coil groups as frequently as possible, you will have better winding factor. You minimize your subharmonics. So let's just briefly give an example to help this make sense. Suppose Q equals 17 by 5, and you can rewrite this as 3 plus 2 by 5. That means Z prime is equal to 2, N is equal to 5, and G is equal to 3. And so we know that we want to have 2 coil groups with G plus 1 coils. So we want to have 2 coil groups with 4 coils, and we want to have 3 coil groups with 3 coils. We came up with 3 because that is N minus Z prime. And since we want to alternate as frequently as possible, we could, for example, pick our sequence of Q values like this, where we've alternated the number of coils between consecutive coil groups as much as we could. Q1 had 3 coils, Q2 had 4, Q3 had 3, Q4 had 4, and Q5 had 3. And depending on the value of little q, this may be more possible than other times. So for example, if Z prime was equal to 1, but N was 5, we would only have 1 coil group with 4 coils, while the rest had 3. And our final step is that we're going to assign Q1, Q2, Q3, all the way to Qn slots sequentially to the U plus, V plus, W plus zones. And then we're going to determine what U minus, V minus, and W minus should be, how many slots reside in those zones. And I think that the easiest way to see this is to unroll this zone diagram. It's hard to draw it as a circle all the time. It's easier to draw a table. So if you unroll this to a linear diagram, you have a table. You have a table where you have a U plus column, then a W minus column, then a V plus, and a U minus. And in each column, you indicate the Q value that is going to reside there, how many slots are going to reside there. And so let's do that. And so you'll see what I've done here is I've made this table and I've put in the columns our sequence of zones. And so this is a familiar sequence. It should be a familiar sequence to you by this point. We go U plus, W minus, V plus, U minus, W plus, V minus, and that spans one set of poles of the machine. And then we repeat this for the second set of poles, and we keep repeating this so on and so forth all the way until we make a complete revolution around our stator. Or what we can do to save time and effort, and I highly recommend this, is that we only do this for the base winding length. So oftentimes these single layer windings are used for very high slot and pole count, and you can save yourself a lot of time and effort by only laying out a single base winding and then realizing that the base winding repeats until you have got the complete stator winding. So again, this is each of these segments is one pole pair. And so if you do it for the whole base winding, you'll do it for P star repetitions, where P star is the number of pole pairs in your base winding. And we talked about how to calculate that in a previous video. And so what you're going to do following this step 4, this whole plot is to illustrate this step 4, is that you're going to assign your Q values to the positive phase zones, and then you're going to figure out what they had to be for the negative phase zones. So we'll start with Q1 in the first phase zone, and then moving to the next positive phase zone, we'd have Q2, Q3, Q4, and say that N was 5, you'd get to Qn, which is 5, and then you just repeat this. You'd repeat this until you've got your full base winding laid out. And so now what we need to do is figure out how many slots need to be assigned to these phase bands. And we'll do that by realizing that our coil needs the same number of coil sides on both sides. So if we have got Q1 slots here, our next phase zone of U minus must also have Q1 slots. And I'll label this with a prime. I'll say this is Q1 prime because it's the return coil side. And we can say that V plus has got Q2 slots, therefore V minus must also have Q2 in it. And then you can start to realize that this just is the same sequence but increasing with primes. And if you were to carry this on, you'd recognize that your first W minus slot must have Qn prime in it, because this base winding is not complete until you end at the end of your sequence of Q values. So really, if we had sketched this for a complete base winding, this would have been Qn right here instead of Q1. So this is our complete design procedure for single layer windings. It's these set of steps here. And the final step in this set of steps is more clearly illustrated right here as this table. So let's go back to our example of a 6-slot 4-pole 3-phase motor and lay it out as a single layer winding. We've already verified the symmetry conditions. Let's now proceed to do our design steps. So step 1 was symmetry conditions. Now we'll do step 2, which is to write Q out in this form. And we get a G value of 0, Z prime equals 1, and N equals 2. Now we'll do step 3, A and B. So we'll figure out how many coil groups have G plus 1 coils, and how many coil groups have G coils. I'm glossing over this step of making sure that our number of coils alternate between consecutive coil groups as frequently as possible, because we only have 2 coil groups. In this case, there's no choice here. They have to alternate between each coil group. And so therefore we get a Q1 value of 1 coil and a Q2 value of 0 coils. And so now we're going to construct this table to assign the coil groups to the slots. And before we do this, we can do some calculations to figure out how long our table needs to be. And we do this by determining our base winding length. So T, which is the greatest common divisor of Q and P, is going to be the greatest common divisor of 6 and 2, which is equal to 2. And then P prime is going to be P divided by T, which is just going to be 1. And since N in this case is an even value, we know that we have a second grade winding. And for second grade windings, we know that our base winding length needs to be twice the value of where our magnetic conditions repeat. So that means that P star, the number of pole pairs in our base winding, needs to be equal to 2 times P prime. And when we talked about this, when we talked about base windings, and it's summarized in the table in your textbook that has the parameters of base windings. Okay, now we're ready to start assigning coil groups. We know that our base winding has to repeat twice, so therefore we have 2 repetitions of this. Here's our first pole pair, and here's our second pole pair, because our base winding has 2 pole pairs in it. And so we've got 2 coil groups, so we'll just keep assigning these in sequence. We need the return side of our coil groups, so they will be over here. And to make our lives a little bit easier, we're going to add a couple more rows to this table. We need to figure out how this table maps to the actual winding layout schematic, and that is what slot number each of these phase zones spans. So where what slot number the phase zone starts at and what slot number it ends at. And we can start by filling in the number of slots, and that is just what the numeric value is for Q1 and Q2. Remember, Q1 is 1, Q2 is 0. So our first phase zone has 1 slot. Remember, this is just a mapping. This table just represents this diagram, but unrolled. So our first phase zone, U plus, has 1 slot. And then our table tells us that our second phase zone, U minus, has 0 slots, and our third phase zone, V plus, has 0 slots. So what we're effectively doing is we are shifting these 2 phase zones over here so that there's no slots in there, and then U minus is shifted over here so it has 1 slot in it. And then so on and so forth. We have 1 slot in each of the next 2 phase zones, no slots for a while, so these get shifted over, 1 slot in each of the next phase zones, and so on and so forth. And so what's helpful when we want to actually lay the winding out is to keep track of the slot number at the start of each zone. And so we do that by just adding these up. So we clearly are starting at slot 1, and then there's no slots here and here, and then we start at slot 2 over here, slot 3, no slots here, 4, 5, and finally we get to slot 6. And at this point we have all the information that we need to actually construct our winding schematic. So we'll do that quick, and we'll show all 3 phases this time. So first I've put a coil for phase U on here, and we can see that phase U has got slots 2 and 3, which is exactly what we've indicated for this coil. The next coil to consider is phase W, which occupies slots 3 and 4. And the next coil to consider is a coil for phase V, which occupies slots 5 and 6. So we now have our complete winding layout. We followed these exact steps of our design procedure, and we constructed this winding layout. Before I close on this, I want to go back to the zone diagram that we did for the double layer winding and show how this has been modified by our design procedure to become a single layer winding. And so what we've done is just working off of our winding schematic here and adding those labels as we go around to the slots is the following. And we've again ended up with a concentrated winding, but the winding coil side placement does not match what we would normally expect based on our zone diagram when we have evenly distributed zones. And so we see that for the negative coil side slots. So normally slot 2 would be assigned to a V plus coil side, but in this approach it's assigned to a U minus instead. Normally coil side 4 would be assigned to U plus, but now instead it's been assigned to W minus. Similar for coil side in slot 6. It would normally be W plus, but now it's V minus. And so effectively what this has done is it's shifted these phase zones over. So it's crammed the V minus and W minus coil zones in before the U minus. So it's shifted the span to be very small for these phase zones. And then we regroup over here at W plus is where we expect it to be. But now again on the other side, we've shifted our phase zones over, where V minus and U plus are crammed into this region so that we can have our W minus phase zone shifted up over here. And then on the bottom as well, U minus and W plus are crammed into this area so that V minus is able to span this slot. So the final thing I want to point out is that single layer fractional slot windings do not always have the same span of coil in all coils. The winding that we just considered right now does actually have the same coil span in all coils, and in our class we've always been saying that double layer windings will have the same coil span in all coils. But you can see that for fractional slot windings, when you use this table, sometimes you're going to have coils of different spans. So in this simple winding case, clearly it didn't happen, but your coil span is going to be determined by the Q values that occur between this phase zone and this phase zone. So if this value right here is different than this value over here, you can see that you'd get a coil that has a different span in different coil groups. And we'll give an example of that in a later video. So in summary, this video has established design procedures for single and double layer fractional slot windings. The double layer winding was very simple for us. It basically was the same procedure we've already been using, but adding a check of the symmetry conditions. The single layer winding was significantly more complicated. We had to come up with a new approach to thinking about winding design, which gave us a very different set of design steps. And this had a focus of going back to our phase zone diagram and distributing the phase zones differently amongst the slots, having a different span for each phase zone. And finally, we concluded with an example of a single layer fractional slot winding.